My name is Max Coletta. So far, we've seen a lot of great data about DOS attacks and neural networks.
We need to switch you over to the, I'm sorry.
No rejection?
Myself.
Excuse us for a second. This is the first thing they ask you at the customer service center. Is it plugged in? Okay. Well, that's a lot better. So I'll take less of a maybe an empirically data-driven approach and discuss a little bit design approaches that we're taking dealing with distributed malware source attacks. This is joint work with Andrew Garlick and Robert Morris, among others, at Mazda Networks in Cambridge, Massachusetts. So there's two questions that I want to address today. One is, if you were local, the other more global or distributed. So the local question is, can we look at traffic on a link that we deem to be congested or possibly under attack and try to distinguish with some fairly high probability traffic that's part of the DOS attack and traffic that isn't? And the second question is, given that we have, assuming that we can build security, is there a way to build a distributed monitoring and tracking infrastructure for malware source attacks that can be deployed in a practical and incremental way? So, first of all, just a few words about the way that we are approaching this problem and why it's so difficult, and why there's three talks today about it. As far as my interpretation of the matter is there's conceptual and practical issues. So conceptually, of course, everything in a packet except for the destination address can be spoofed. So trying to statically filter based on anything other than a destination address is probably unlikely to work very well in most cases. At the same time, people most willing to install filters to try to stop malware source traffic, mainly the victims, probably don't want to install destination address-based filters next to the network, but that would simply reinforce the DOS attacks. And finally, there's an issue where if you want to move the filtering upstream so as to make destination-based filtering less punitive for the victim itself, then that would require communication, which in turn probably requires an authentication mechanism, and so forth. So, in addition to these conceptual problems, there's practical ones. Riders certainly these days don't have our extra cycles for traffic analysis or filtering. This problem is likely to get only worse as network speeds increase. Furthermore, as I'm sure a lot of you are intimately familiar with, there's a network stability requirement, so biases against changes to the infrastructure. In addition to political problems, we're trying to track and attack across multiple domains using they talk to each other. How do we address that? And finally, there's really, I think, a mismatch in perspective between people who operate networks, typically with very large bandwidth, and victims who can be disabled by relatively small flows of traffic. So despite all these issues, the goal is to maximize the ability to filter identified by traffic and minimize the collateral damage, the filtering of traffic that instead we should let through. So going back to our agenda, answering the first question, the goal is we look at a network link, and what we want to obtain is some dynamic signature, some information about the attack traffic from which we might possibly be able to build a filter, somehow stop this flood. And so what I'll be talking about is algorithms and heuristics that we've developed and actually implemented at Mazu, and describe how they work effectively. So the general category of the general name that we've given to our approach is historical aggregate analysis. The term aggregate I've borrowed from Steve Belvin and others from their aggregate congestion control work earlier this year. So aggregate refers to a set of packets that share some properties. So for instance, all DNS packets are all packets from a certain source. And the original focus of the aggregate work was focus on destination addresses and rate limit effectively traffic going to high volume destination addresses. So this is a great idea if you're trying to protect the network. It will work fine. But of course, it only increases the denial of service attack on the victim. And furthermore, it doesn't work well if you try to compute aggregates on parameters that can be randomly spoofed, so things like source addresses. So our approach is a variation that sort of is twofold, and there's two branches to our work. The first is to use multiple parameters simultaneously to compute aggregates. So look at things like packet length, TTL distributions, even hashes of packet payload. And the second is to look at distributions of these parameters over time in an attempt to decrease collateral damage. So the question you might be asking at this point is sort of how can history be useful? You know, what do we get from looking at historical data? And the intuitive insight, which we've also confirmed from collecting data from order of a dozen networks over the last year, essentially, is that in fact many parameter distributions tend to be relatively stable. They don't change very much over time. So an example, actually, unfortunately, I see that the plots don't show up very well on the projector, but I'll describe them. The two plots that you see are address distributions. So the x-axis is IP address space from all zeros on the left-hand side to all ones on the right-hand side. And the y-axis packet count, and what's being counted is source addresses of incoming packets and destination addresses of outgoing packets for a particular Q1 line. And the data that you see is over a period of 2 months on the top graph and over a period of essentially a day for the bottom graph. And what you'll notice is that, in fact, that the graphs look very similar, and that traffic that isn't seen during a day typically isn't seen during a longer period. And conversely, regions that have traffic during a long period tend to also see traffic during a shorter period. And this data holds across many network locations where we've had the opportunity to observe traffic, and it seems to hold across multiple parameters. So for instance, source addresses, TTLs, many other things tend to be clumped, and they tend to be consistent at a given location for scales, time scales that are relatively long, so longer than about a minute or so. And so the intuition that this might lead you to is that in the worst case, if you're looking at some parameter and you're trying to minimize collateral damage, you're trying to minimize the filtering or negative reinforcement that you do on traffic that actually is not part of a DOS attack, then one way of trying to limit that collateral damage is to actually look at the long-term path distributions for guidance, and therefore, then first apply filters to the biggest outliers that we see in our current traffic, or maybe to values that are to regions of the parameter space that are historically low. So here's an example. What you see on the top, in both cases, both images, the axes are the same as in the previous slide. And what you see at the top is a source address distribution for incoming traffic for a large website, something that sees on the order of 500,000 packets per second sustained during the day, collected over a period of a few days. And the bottom is what you would typically expect to see during some sort of randomized flood. In this case, it was a scent flood that we were measuring, where source addresses have been spoofed uniformly. And so, going back to our previous intuition, what we might do here is, being able to pick no source-based aggregate on which to filter, we could simply try to effectively shape the traffic that we're seeing incoming relative to the path distribution that was obtained over a long-term path period. So the previous slide had a spoofing example, and detecting spoofing is interesting for a couple of reasons. There's certainly just an information gathering or forensic aspect to it, but it can be used as a guideline to help us determine whether in fact it's useful to spoof, to filter or try to track attacks based on high volume aggregates in the style of development, for instance, or whether a history-based approach is more appropriate. So one way to try to determine this is, for instance, to look at the variance or the standard deviation of the histogram buckets for parameter histograms that we collect. So going back, looking just for a second back up at the previous plot, you'll notice that in the top figure, there are some groups of addresses that see a lot of traffic, others see almost none. So you'd expect standard deviation to be relatively high if we look at standard deviation of the actual bucket values, the bin values of the histogram. And conversely, for the bottom plot, there's not a lot of spread, so standard deviation intuitively is low. We can divide by the mean of the traffic that we see during the period of data collection in order to normalize for differing traffic volumes. So for instance, you can compare traffic seen at night when data collected at night when there isn't much traffic to data in the middle of the day when there's more traffic. And then intuitively what we obtain is a metric where lower values imply more randomness, a higher degree of spoofing. And this is, even though again the bottom plot doesn't show up very well on the projector, this is comes through in these plots. So for instance, what you need to look at is the y-axis of these parameter values. The x-axis again is time. So this parameter computed over a period of a day for the large website. You see values are approximately in the range of 10 to 15, whereas for completely random uniform spoofing, the value drops to far below 1. To and show you another parameter, another example to illustrate our approach, let's take a look at TTLs. So different IP implementations will set their initial TTLs to different values, typically powers of 2. And so if you look at incoming traffic, and this plot was, the top plot is TTL values on the x-axis for incoming traffic, and the y-axis is packet count into a large data center. And you see that there are spikes at all powers of 2. And the width of the spike, if you will, indicates the diameter of the internet, if you will, at that particular data center. And this plot is extremely stable across different time periods. And it sort of indicates a certain approach for detecting whether we're seeing spoofed traffic or not, or in general attack traffic. Because if an attacker is actually not very clueful and decides to completely randomize the entire packet except for the destination address, and therefore also including the TTL, then we'll see all sorts of packets in the big empty regions where we know that it's very unlikely that that's actually legitimate traffic. And by contrast, if, for instance, we have a reflector attack where a whole bunch of machines at one particular data center that's a given number of hops away from the victim, if someone launches the reflector attack that's reflected from that data center, then there'll be a big spike, presumably, from the TTL corresponding to that data center. And again, we can detect that spike either by direct inspection of the histogram or by looking at metrics like the ratio of standard deviation to mean, as evidenced in the bottom plot, and use that to filter out the traffic that seems improbable, hopefully incurring minimum collateral damage in the process. And another example is packet length. I'll skip over it in the interest of time, since we do seem to be falling a little bit behind schedule, but again, the intuition is the same. To look at historical distributions, notice that there are patterns that remain stable at given locations over time for different time scales, and then to use that to help us select the aggregates or sets of packets in which to that we suspect should be part of the DOS attack. Okay, so at this point I'm going to switch over to the second part of the talk, the second question on the agenda, if you remember. So let's assume that we can identify with a good degree of probability sort of distinguish traffic that might be caused by a DOS attack versus traffic that's probably legitimate on a particular link. So now, of course, the goal is to try to identify, for instance, where that traffic's entering our network and possibly even move as close as possible to its source. So there's a way to deploy an infrastructure that can perform this task in a way that's sort of practical and incremental given current constraints. So again, to remind you of constraints that I listed earlier, a limited router computation budget is certainly one, operational bias against network change, and then the fact that attack tracing might involve multiple administrative domains and therefore incur all sorts of potential policy or human collaboration issues. So our approach is to minimize the change that needs to happen to existing infrastructure. In particular, the goal is to not poke devices that are on the network at all, and to try to minimize communication between different administrative domains, so for instance, between different ISPs. And this piece of slideware here, which I'll use to give an example of how the protocol that we've implemented actually operates, is sort of to illustrate the infrastructure, how we plan to deploy. But the idea is that at the bottom level, there's already deployed infrastructure, routers, switches, and so forth. The goal is to passively monitor links that are major egress or ingress links to particular networks, have the monitoring infrastructure communicate among each other, and then to define a well-specified set of machines that we call NOC servers to allow communication between different administrative domains. So to give you a quick example before I move into some details and some motivations for design decisions that we've made, let's assume in sort of circle number 1 that an attack is happening on a link. And assume that a passive monitor that's looking at traffic on this link using some set of heuristics detects that there is an attack and comes up with some signature, congestion signature, and attack signature that describes the traffic that's probably causing the attack. That information is then communicated in step 3 to what we call a NOC server, which effectively takes this information, generates a set of queries that, for instance, might be, is anyone seeing traffic of this particular kind, say UDP traffic with that uses these particular ports or has such and such payload hash, and takes this query and propagates it to both other domains, so other peer NOC servers, and to other monitors. And it's in this information, the data collection happens in a completely distributed manner, and this information can then be returned to the querying NOC server, which can then provide essentially information about ingress and egress points of the suspect traffic to an operator. This is just text of what I said, and really what I want to move to is motivations for this design, which, as I said, we've to a large degree implemented. So there's really 3 categories of design criteria. There's design criteria for the individual monitoring technology, like how do you obtain information about attacks on a link. The second is design criteria for how the devices communicate. And the third is really design criteria for filtering. How do you implement filtering? So the first thing that we believe very strongly, and I guess this is in contrast to Rob in the previous talk, is that tapping links is actually operationally the least intrusive way of doing things. We've tried, again, both approaches, and I guess both Rob and I have contrasting anecdotal evidence, but certainly many operators of large, heavily loaded routers don't like it when one tries to obtain information from those routers. So it appears that tapping the network at the link level with, like, for instance, fiber splitters is the least intrusive way of doing so. This also provides us increased visibility into traffic, because if, for instance, the data collection method like NetFlow or CFlowD that we use to get data from a router doesn't return, say, TTL information, we can do that through direct packet inspection. So it seems like a more general approach. The second decision related to monitoring devices is that really they should be storing state. First, because this enables historical analysis, which, as I argued earlier, can help to decrease false positives and collateral damage in general. And the second is that that can help to minimize inter-monitor communication. So some schemes have been proposed where edge routers actually send traffic which they deem to be suspicious across, for instance, IP tunnels to some central collecting agency, which then tries to determine whether traffic is the cause of a DDoS attack or not. And that seems to actually potentially cause DOS attacks on the monitoring network itself. And the idea behind having storage of monitors is to enable each monitor to perform analysis independently and then simply reply with, short yes/no type answers to a central information gathering location. So talking about communication, I believe that hierarchy is key, because providing a hierarchical network can simplify inter-domain administration. It's much easier for each ISP or AS to have, 1 or 2 machines that talk to other ISPs or ASs about the potentially harmful traffic that they're seeing, rather than trying to create a vast authentication infrastructure that would allow monitors or edge routers that arbitrarily deployed in an ISP to talk to all other such devices at other ISPs. And even though it's not really a design decision, it's something that I think we very much advocate is an open standard for communication, because all these devices, whether they're embedded in routers, whether standalone monitors, in the end, if they don't communicate if they don't have some open standard with which they can communicate, risk becoming useless and really not being deployed very widely. And the final bit of religion that I'll claim today is filtering policy. And really there's two key things there. The first is the need to separate filtering from monitoring. It's much easier for me as an ISP operator to ask my peer ISP whether they're seeing a certain kind of traffic and to help me track that traffic across their network than it is to try to impose a filtering strategy as part of that tracking mechanism. So the two really, I think, administratively need to be separated. And then the second filtering design criterion is that there should be really a human in the loop during filtering. And if that's not the case, then really we're opening ourselves up to people who are potentially smarter than the designers of the monitoring system or the filtering system to create DOS attacks implemented with the DOS filtering system itself. And so the two proposals that have been most, I guess, influential in our design were traceback and pushback. Both of these at some level are very elegant because they make monitoring part of the network itself. But the thing that really we wanted to minimize, that's not minimized in both these designs, is the changes to infrastructure that is already deployed today. So for instance, software changes to routers. And then really the other important thing was to try to separate very cleanly filtering policy from monitoring policy. Of course, distributed monitoring, as we call it, has its own challenges. The first, of course, is that it requires deployment of new monitoring devices. And really we see this as a trade-off. Either you change infrastructure that's there that works and that most people don't want to change, or you need to effectively deploy new devices that are, perform the specific monitoring task. As far as filtering is concerned, there really seems to be no free and easy solution. If we try to filter via routers, for instance, by creating ACLs, for instance, that might be used, or committed access rate type things that can be used to filter traffic on routers, then we risk decreasing router performance. And furthermore, we're limited by the expressiveness of the ACL language itself. If the router doesn't allow us to filter by TTL, then there's no use to using TTL-based heuristics. Using a dedicated device to filter can solve both of these issues, both the speed and the expressiveness, but of course it introduces a new network element. So nothing seems to come for free these days. And the final challenge really for any scheme that attempts to do distributed DDoS analysis is to generate momentum on some sort of open standard for communication between these devices. Just a quick word on our own sort of implementation status, if you will. The heuristics that I described today, as well as several others, are implemented. Devices that run them can monitor up to 8 GE links at about 1 million packets per second per link. And we've had a fair degree of success deploying on a number of commercial networks where we've actually been able to identify and help users debug denial of service attacks. The first version of the monitoring protocol that I so roughly described earlier is actually implemented. And really the focus the area that we're focusing on most is improving the detection heuristics and also building filtering functionality. So in conclusion, I think that combining aggregates, sort of in the style of Steve Elvin, with historical information and using multiple aggregates to try to categorize traffic is a promising method of identifying denial of service traffic while minimizing collateral damage. And that a scheme like distributed monitoring that actually imposes relatively little change to existing infrastructure and minimizes inter-domain communication is probably a reasonable way to go to try to address DDoS in a distributed fashion. And finally, the last thing I'd like to leave with you today is really that interoperability between devices that perform distributed DDoS analysis is the key to their success. And with that, if you have questions, I'd be happy to field them. Questions? Oh.
Thank you.
One quick question before you leave.
Yep.
As we saw, the ambient level of attacks on the network seems to be at a fairly high level just on a day-to-day basis. And most of these systems seem to be extremely good at detecting the attacks and telling me I'm being attacked almost constantly, which is not a very useful piece of information.
Yep.
How well do these systems are at prioritizing attacks and telling me what are the big attacks, or how well can I tell them, tell me when this important thing is being attacked, as opposed to just picking up every single DDoS on my network?
Well, can you hear me?
Yes.
So it's really a question of, at some level, threshold setting. So, you know, the kinds of things that for instance, one possible thing is to look at simply at link capacity. And one possible way to define a DDoS attack, or for that matter, a flash crowd, is to look, for instance, at congestion on a router or high utilization on a link. At that point, you know, a small ISP or a home cable user could, you know, obviously has a different notion, a different threshold for what suspect levels of traffic are relative to, you know, what a big backbone might have. I'm not sure if that answers your question. I mean, there are really two separate problems. There's a problem of detecting, am I under a DDoS attack? And the second one is, you know, assuming that I am under a DDoS attack, then let me look at my traffic and try to figure out which packets look suspect and which don't. And the point that I mainly addressed in this talk was the latter. So assuming that assuming that the link is congested, are there things that I can look at in the traffic, sort of just by observing that link, that help me, you know, give me some indication as to what might be unusual and therefore possibly bad, and what actually isn't unusual. The question of whether you're under DDoS attack or not is really a function of if you're worried about bandwidth attacks, then it's whether you're congested or not. And if you're worried about things like server attacks, like running out of, you know, TCP control blocks or whatever, the SIR floods, then you really need effectively information about server state.
How do you think DDoS or DOS attacks are in correlation with flash crowds?
Flash crowds. So the question is, how do DDoS attacks correlate with flash crowds? Like, what is, how can they be, how are they different or the same? I guess so again, going back to the previous theme, detecting whether you're under a DOS attack, and then the second question is, you know, what are the DOS packets? So it seems to be quite difficult in general to distinguish, you know, when you see a traffic spike, to distinguish immediately whether that's a flash crowd or a DOS attack, except to the extent that you can predict the flash crowd because it might be related to marketing efforts or, you know, publicity or whatever. Now, as far as once you've entered a suspicious state and you decide to look at traffic to see whether it might be a flash crowd or a now service attack, in the limit, a very, very smart attacker that knows, you know, what the TTL distributions into your site look like, what source addresses you see, and so forth, might be able to engineer a DOS attack that actually looks indistinguishable from a flash crowd. But chances are that, you know, most tools, at least for a while, will generate attacks that are distinguishable, at least in a few subtle parameters. Okay. Yeah, and of course, if you just one more thing, I guess in the limit, the worst kind of DOS attack, the one that you probably do least about, is if people, you know, all listen to, I don't know, the BBC, you know, shortwave radio, and when it's noon in London, everyone hits reload on their browser, right? Then there's really not much that you can do aside from you know, some sort of red or, you know, other kinds of fair queuing on routers.
Okay, and if I understand correctly, you're saying that ACL in routers is not a very successful solution.
Yes.
But on the other hand, if you have to add a device, this means now I have to put this all around my AS. Is that correct? And it has to be on the way of the main routers.
For filtering,
I'm talking about the filtering problem. I mean, the
yes,
thing is one thing.
the filtering problem is a difficult one. And yes, I mean, that's, you know, either you can do it many different ways. You can, today the simplest way is to install an ACL on your router. It probably won't work for many kinds of attacks, or at least probably won't work in the way that you'd like it to. For instance, by you know, one thing you could do is filter, of course, by destination address, and that would just completely punish the victim. Another thing is actual router hardware changes. So, for instance, some sort of high-speed filtering blade, but I'm not sure how far away that is. And then, of course, there's deployment of devices on every link. And yes, certainly it's a logistical issue.
Okay, thank you.
In your last answer, you mentioned active queue management briefly. And I was wondering, in your last answer, you mentioned active queue management briefly. I was wondering if you're aware of any research in using your normality filters, as you were discussing earlier, as a way of weighing an active queue management algorithm in the case of a bandwidth-consuming attack towards the edge, where an edge site could choose to drop packets on a congested link that don't fit the normality filter, thereby reducing the negative impact of an attack, although it wouldn't stop the attack. And I haven't seen any research towards actually doing that. That would be something that could be deployed more towards the target of the attack without as many network infrastructure changes.
So I'm actually, to be honest, I'm not completely. I'm not familiar with such research. I don't know that any has been done. I'm not completely sure I understand your point. You might want to talk about it offline. Certainly, queue management based on historical information might be useful. Again, the fear that I have there is that if you try to automatically drop packets based on history, then you can get into possibly very problematic.
Well, if you're talking about doing like ACLs based on historical data, I can definitely see the room for problems there. But if you're looking at a congested link, a packet has to be dropped. There might be an advantage to weighing that drop based on the normalcy of the packet rather than just first in, first out, or another probability metric. So. Yeah,
well, again, you know, I think unless in that case, things like red, I think, you know, things that are completely random, or, you know, with probability changes based on the queue length, seem like they're the least likely to introduce sort of vicious side effects that might be exploited for other purposes. I think if we really try to be smart about filtering and use things like history or whatever, then that can be very useful. And I mean, that's really what I'm advocating. But I think it's something where a human needs to be involved, or else you run into trouble.
Okay. Thank you.
Yep.
Thanks, Zach.